They were
I
the
haven't
raw
noticed.
data. Okay, I need to see where the TA posted them. So they are the raw data from each of you for each team. So I asked the TA to kind of put it all together per team, and it's posted per team. So I'll see where he put them if you don't see them. Okay, we have just about a minute. If you're ready, we can get started.
Dr. Ruby, I have one question before they start.
Sure thing.
I think I missed when you said it. Is there's still peer evaluations for these, correct?
We're not doing them today. If you'd
Okay.
like to do them, of course you're welcome to for bonus, but we're not doing them today. So just sit back, enjoy the presentations, do some critical thinking. I'd like for you to, stay involved. And I expect to hear some questions at the end for each.
All right. Thank you.
You're welcome. All right, give me just 20 seconds and then we can get started when everyone is ready.
Real quick, I'm going to apologize ahead of time because there's people working outside and my dogs do not like that. So if they bark in the background, I will try to get it handled.
That's not a problem. All right, we have two. Just writing the initials down. So all right, whenever you're ready. Your time starts when you start talking.
All right, we are the modular cardio machine for exploration missions. Our participants are Charles Shepard, myself, Dakota Horvath, Enrique Herrera, Jacob Davis, Jesus Hernandez, and Patrick Huddleston. Our project mentor is Dr. Jose Baca. This is our outline we'll be going over today and will be discussed. And I'll pass it off to Patrick with the introduction.
All right, welcome everyone. Today we'll be talking about our project. So to introduce it, I'd like to first start talking about the problem that we're trying to solve. So the team is tasked to create an exercise machine that's meant for future space missions that's improving on the current design, which is the T2 treadmill that's currently residing in the International Space Station. Our new design is supposed to provide the same physiological benefits as a treadmill, but it needs to have less mass, a smaller volume, and also need lower power consumption. Next slide. So for the background on this project, researchers from NASA found that the ground reaction force due to gravity when you're running is crucial for the astronauts' musculoskeletal health. But of course, in zero gravity, this needs to be simulated. So NASA is looking for an alternative to a treadmill since it's too bulky for deep space missions. And also the harness that's being used on the current model causes discomfort during its use. Next slide. So two of the patents that inspired our design, on the left you can see is a foot skate type elliptical design where it slides back and forth. And you'll see the inspiration later on. And on the right you can see an alternator hooked up to a bicycle that powers the system. Next slide. So here's the design that we've proposed. It resembles a commonly used elliptical machine, but we added sliding retention boots along the rails, as you can see in the bottom right picture. The way we're simulating the impact is that the boot is going to slide to the right, impact the right stopper, which pushes the small flywheel. And as you step down, the boot slides to the left, impacts the left stopper, which pushes the large flywheel, and that completes a full cycle. Not shown in the drawings is an alternator that will be used to charge a large battery pack that can be used to power various things on the ISS. Next slide. So during our design, we'll need various hardware such as aluminum flat and round stock for the main construction, hardware such as nuts, bolts, and washers, ball bearings, fabric material for the boots, an alternator for powering or for charging the battery pack, and copper wire for connecting it all together. The standards that we'll be using in this project is that we'll be using the metric system and also the NASA's low Earth orbit charging systems for the battery pack. And as you can see on the right, there's also a diagram for how we're going to charge it. And now I will hand it off to Dakota.
For the feasibility of this project, the economic feasibility, there's only enough money for a proof of concept and a basic working prototype, not something we can actually send to the International Space Station. Our technical feasibility, there's enough resources and skills between the professors, our mentor, and the team itself for a proof of concept and working prototype. Socially, it'll have a small impact as it's really only going to impact the people aboard the International Space Station. Health and safety, we'll be designing this treadmill with safety firsthand in mind. And as far as health, it's up there for the people on the International Space Station to be healthy and move. Environmental, again, it'll be impacting the people in the International Space Station the most. They'll gain new equipment to work out on replacing their old treadmill. Next up is the work breakdown structure. We have the modular cardio machine up top, broken into mechanical and electrical components. You have the alternator on the electrical side, which is to create and store power on the International Space Station. You have the strap-in boots, arm supports, flywheels, sliding braces, all on the mechanical side, with their actions as well listed below them, such as keeping inertia moving for the flywheels and supporting the boots while exercising for the sliding support braces. Next up is Jacob with the linear responsibility chart.
All right, so this is the linear responsibility chart that we created. It'll show everybody that's associated with the project, and then who's responsible for which tasks, who support each task, and then who we're going to notify and seek approval for. Next slide. So this is the first part of the task and timeline that we created in Microsoft Project. It's the Gantt chart. And this part just kind of shows that the initiation phase is complete. The planning phase is still underway, which we're trying to wrap up and move to the implementation phase. Next slide. And this is the second part that kind of shows the implementation phase kind of broken down into like the build, test, improve, and then final testing leading to the termination phase. Next slide. For the resource allocation, we created a resource overview report. Previously, we had underleveled and overleveled resources, so we've since distributed the workload a little bit more evenly to where it just balanced the workload between all the team members. Next slide. For the expected budget, we created a resource cost overview report in Microsoft Project again. It'll show you that the main bulk of the cost distribution is going to be the work from the resources. Now on the right side, you'll see the bill of materials versus the expected budget. The bill of materials, this project would cost like $146,000 if another company tried to replicate it. If they used all the same things that we're going to be using. But for the expected budget, it came down to $185 because a lot of that is going to be in kinds. But we do have $300, so if anything were to break or anything like that, we do have a little bit of wiggle room. Next slide. For the implementation phase, our plan, we really highlighted the implementation phase for the Gantt chart. Goes into the build of all the different mechanical aspects, the electrical aspects, and then the testing of each of the subsystems, how we're going to integrate them together, and then retest whenever they're already integrated. Then we're going to try and improve the mechanical and electrical aspects, leading to the final testing and then the termination phase. And I'm now going to pass on to Jesus.
For the testing and evaluation plan, we plan on conducting structural and stress analysis of the frame, testing of the electrical components and of the resistance system. Once it's assembled, we're going to conduct prototype testing, operational tests, and try to simulate zero gravity testing. And for evaluation and validation, we're going to do 3D tracking with the aid of software, physiological and cardio testing, and make sure it meets the dimensions and mass and power consumption outlined by the NASA standards. Next slide. The risk management plan, we've identified 5 risks, scaling from 1 through 5. The number 1 being that our concept does not meet NASA expectations. The second would be falling behind the schedule. Third would be lack of technical knowledge. And fourth would be that we're unable to conduct proper testing. And last would be that our cost exceeds the budget. Next slide. The monitor and control plan will be done with the aid of various reports, AOA charts, Gantt charts, the project schedule, and value graphs, and also the work breakdown schedule. Now I'll pass it over to Charles.
As you can see, this is our action plan for the next few weeks, all the way up to our final presentation. And for our resources, we're going to be using a lot of the engineering lab and our mentor, as well as other materials we can gain from purchasing and other ways. Next slide, please. For our audit and response and termination plan, we are currently still in the planning phase. We are behind schedule, currently working towards our blueprint design. For the potential risks, the cost may exceed the budget, but as said, we have $185 scheduled for it, but we have a $300 budget. And another risk is we could fall further behind schedule, or we don't meet the standards for the NASA. Some of the limitations we have, because we are behind schedule, we can't fully expand on the other sections of the project that we haven't gotten to. But for the termination plan, like I said, we are behind schedule, but we are still on the road to hitting the projected termination date. So nothing's changed that way. So I'm going to hand it off to Enrique.
All right, so here we have the activity on network diagram. As you can see here, we have a little flow in alphabetical order showing from this process from start to end. We have here the legend there on the right, as well as shown in alphabetical order with our activities that we have done and with the duration of the days, which will be also related to the length of the arrows shown in the diagram. Next slide. Here we have the value analysis chart. We have here most of the hardware that we're going to be using and the quantity of each that we're going to be using along with the cost. Next slide. And to conclude, we got rid of the old design as you saw in our last presentation, and we have this new design that was presented in the beginning slides. We still are required to meet the standards for NASA with this new design. So we are working to hopefully meet those standards. And as far as the feasibility, we will be having a working prototype, but unfortunately, since this equipment is supposed to be to use in space, to help us out, we're going to have a virtual reality software will be provided with the engineering building to help us out with demonstrating how it would work in zero gravity. Any questions?
Okay, let's take questions.
So one question I do have, y'all said that one of the problems with the current design of the treadmill is the harness. Are y'all just going to use the boots to secure the individual in place?
Yeah, so the boots will be for the impact, and they will be for securing the individual. Also, we'll be using the poles for stability.
Okay.
Yeah.
Any other questions or comments?
I have one. Would this be easy to repair in space if it broke?
So we actually thought about that. Did you want to take that, Dakota?
No, go ahead.
Okay. So we actually planned for it to be modular. So that means that it'll be more easily repairable, because they'll be able to not just have to tear it apart and try and fix it. They can just replace parts, simple parts that they can just plug and play.
All right.
Okay. Any other questions?
Just one more. As far as the resistance, y'all plan to have any way to change the resistance provided by the machine?
Yes. So we're actually talking about using similar to a bicycle brake, or something else that you would see on the exercise bikes, such as in the Dugan, which is a simple cable driven, use your hand to tighten it, something simple.
Okay. And I guess just kind of follow up on that. Are you going to have a generator on this as well on the prototype?
Yeah, the alternator is going to be connected to actually store charges and batteries up there.
I just wonder if you can maybe increase the resistance on that generator to produce more resistance on the machine and on the person, and then you're creating.
We were actually bouncing ideas about that with Dr. Baca. He wants to try and keep it, or I guess as a team, we've kind of decided to try and keep it as passive of a system as possible. At the same time, we don't want to eliminate the utilization of generating electricity and just let it go to waste. You know what I mean?
Right. Okay. Cool. Thank you.
All right, so at this time we should have our design finalized. Do you have the specifications? What are the specifications? Let's start with what are the requirements, specifications, and constraints for this design? So make sure that you identify those separately, because I want to know that people are aware of the differences between requirements, constraints, and specifications. They all go under project design criteria, but the requirements come from the client, the customer. So NASA is the one who tells you what they want. That's the requirements. And then the constraints are the limitations, if you like, under which this design has to be completed or under which the prototype needs to perform. And specifications are your dimensions as well as the materials that you'll be using. So I see the specs, but they're not specified or specifications. And since you have it on the slide, I also have a note here. Again, you've listed the standards, but you actually have a lot more standards that's applicable to your design. Now that this is for cardio, you're now going to be required to include some biomedical engineering standards that apply to human health. And then also your materials are going to have to be of higher standard because it's going to go to space and you don't want these things to break down. So obviously, and it needs to be probably, light material. So aluminum, I'm assuming, is a prototype replacement for titanium, for example. So there are some standards associated with those that you need to identify. And if Dr. Baca is your best resource, if he's not able to answer this question, then you really need to contact NASA engineers and ask for some help. Okay, so at this time I expected to see a lot more detail on the design. So this is the design you're going with, is that correct?
Yes, ma'am.
Okay, and then you'll be creating a prototype based on this that you can actually exercise on. I know that it will not be up to par to be sent to space, but at least it should be usable on Earth, as so you can test it. Is that correct expectation?
Yes, ma'am.
Yes. Okay. All right. All right, let's go back to the first slide. So what changes did you make to the progress report? Because I don't see a lot of changes.
To the progress report?
Well, to the last presentation, what changes did you make?
With
slide 4.
Okay.
You've done a great job with problem statement. We know exactly what the problem is and what you're addressing. You've also done a great job with the background. You identified the 2 specific patents that are applicable. Make sure that when you are presenting, moving forward, I appreciate that you put the patent numbers under the figures. Can you go to the next slide, please? So you put the patent numbers as you should, but you also need the inventor's name, the title of the patent, and when it was issued. Because if this patent is from within the last 20 years, it's got different ramification than if it was from, say, more than 20 years ago. The IP is valid for 20 years unless they find a way to renew it. Okay, so you want the title. You verbally mentioned it, so we're good there. But just be aware that it needs to, for completeness, it needs to be on the slide. All right, next one. So for the report, I'm going to need to see a lot more views, exploded views, dimensions, description of materials, because obviously not all of this is going to be aluminum, or is it? Well, at least the fastening cords or whatever it is that you're hooking it up to are not going to be aluminum, correct?
Yes, ma'am. Yeah, the main construction will be made of aluminum.
Okay, so I expect to see more details. Since this is your final design, I expect that it's going to have more details in the report. Next. All right, again, we talked about standards. Next. All right, so again, this is for everyone, okay? Please go back and look at the comments I left for your draft presentation, because I spend between 45 to 1 hour per presentation, oral presentation. And the reason I don't grade them until you put your slides in Blackboard is because sometimes my own comments don't make sense to me. So I have to see why I said what I said in my personal notes so that I can give you feedback. So this is a little bit weak in terms of feasibility analysis. It's kind of like your word against the world. So you need to put some evidence for these. So if you're talking about economic feasibility, you need to mention that we expect this to cost $182 and we have $300, so it's economically feasible. And then technical feasibility, you need to beef this up a little bit, because having enough resources doesn't mean that it's technically feasible. Technical feasibility is more to do with, the forces that's going to go on this thing, whether or not your nuts and bolts are going to hold this.
One issue about that is with the draft proposal, we accidentally submitted the preliminary proposal, so we didn't get those comments.
Yeah, okay. All right.
That was our bad.
All right, next one. This is good. Next. All right, I missed the legend. It's there. That's good. Let's go to next one. All right, so the tasks and timeline are missing your milestones, and it is also missing your design. Design needs to be part of your plan, because we just finished the plan for your capstone project and the design is done. So that design is a big milestone and big deliverable for the semesters, and I don't see it on your Gantt chart, so you need to update it. So
it should be on the second page. The blueprint design.
Okay, you guys need to enlarge it. I can't see it. Can you put it in full view?
I do need to make it a milestone. That's my bad.
Okay, where is the design?
Right above the implementation phase.
Okay, but you need a lot more steps for design, because we spent half the semester for perfecting it. So it's not just a one-liner. I mean, I think determining methodology for the flywheels, determining methodology for sliding, those are all part of your design process. So the design needs to go a little bit higher, okay?
Okay, just make it a summary task.
Design blueprint, that should be your milestone. That's correct, which means you finalized it, right? Okay,
yeah.
Next one. Oh, one more thing on the previous one. There's no timeline on this, on the right-hand side. So all those things that's listed on the right-hand side, they're not very informative, because the top side should keep that timeline. All right, next. And I'm telling you these, so that you can update them before you upload them, because I'm telling you what's wrong with them, and then I end up taking points off again because I'm seeing exactly the same PowerPoint. So fix them so that you don't get those points off. All right, this was good. Next. I'm running late, so I'm going to pick up speed here. And I thank you for separating personnel hours and material cost. It is very important for people to understand that material cost is not the only cost that's associated with a project. Obviously, you know, personnel wages is not the only other thing, but we are getting closer. That's usually the biggest cost for any project. Okay, next. Some of my comments is for everyone, by the way. All right, keep going. Let's see. Okay, test and evaluation plan. Okay, a little bit superficial, but okay for oral presentation. Next. So you've listed the risk management steps, and that's great, but you haven't shown them. You need to apply them to your project. So again, make sure that that's done in at least your report. And I'm sure you can come up with a lot more potential problems. There's a chance that if we go on lockdown, we may not access the labs. And so that's actually a pretty critical risk for all capstone projects. That's probably going to show itself up on the upper right corner as one of the red boxes. So you need to figure out your risk mitigation plan if should that happen. Okay. Last year, what some people did was find external sources, like went to companies in order to manufacture things, but you know, that's because they were already either working there or they had some acquaintances who could help them. So just be aware so that you don't get stuck. All right, next. I like this chart. Next. So what I haven't seen are, okay, can you go to the earned value chart? Action plan was good. Next. All right, so this one is, I think, your planned value, correct? So this is your plan, so it follows that S curve, which is good. Is that correct?
Yes, ma'am.
Okay, so I didn't see your actual value, and I didn't see your earned value. So earned value is the value of each task that has been completed. So if you determined that finalizing a design is going to take a month and it's worth, based on the number of hours that you need to work on it, it's going to be about $10,000, okay? And then it ended up, and you finished it, then you earned the $10,000 on that task. So that's your earned value. If you didn't finish it and you only finished 70%, then you earned 70% of $10,000 of that value. Now, you may have finished it, but you ended up spending double the amount of hours and it costs you $20,000. Then your actual cost is much higher than your earned value. So you can then do those variance analyses, the cost variance, time variance, and schedule variance. So again, I apologize, I'm spending too much time on this presentation, but it applies to everyone. So, you know, you want to make sure that you understand that clearly, and if not, touch base with me, okay? But I like this, this is the planned value. You need two more charts on there. The earned value will be up till today, because earned value, it can only happen for past till present. And then same thing for actual. You cannot talk about actual cost until you know, the day, until or that current time. All right, I think that's the main stuff I had. Good presentation, good confidence. Everybody's dressed up, so and good way of handling questions. I'm glad to see that you're pretty close to the final design. It's a bit simplistic for me right now. So you'll need to make sure that you include different views, different cross sections. I saw your circuit electronics diagram, so that's good also. Just beef it up, okay? Because this is your final design. Thank you very much. Good work. And who is the presenter for the next presentation?
Thanks for tuning in, Dr. Baca.
Good job, guys.
Thank you.
That would be me, Dr. Ruby.
Thank you.
Alan.
Got you. Hold on. Okay, Alon, you'll need to move the text out of the print space. Thank you. And your time starts when you start talking. Ready? Do you have all the team members? Can you all hear me?
Yes.
Yes, ma'am.
Hear me. Something happened to my phone. Were you able to hear me?
I can hear you.
Yes.
Okay. Whenever you're ready.
Hello, everyone. This is the Ground Robot Swarm project. This is our capstone project plan, our final proposal. My name is Alon Garduno. I'm accompanied by Kelsey Gleaser, Madison O'Neill, Keila Pena, Nathan Westboro, and our project sponsor is Dr. Paula Rangel, and our instructor is Dr. Ruby Merubi.
Here's an outline of our project. We got our background, journals and patents, proposed working plan, all the way to action plan, activity on node, work breakdown structure, linear responsibility chart, resource allocation, resource leveling, implementation plan, risk management plan, audit response and termination plan, expected budget, EVA, accomplished/remaining work, and the conclusion. As far as the introduction goes, we'll have a robotic swarm that will be programmed to demonstrate a simulated autonomous robot mission in Martian environment. A robotic platform that improves resource retrieval rates by 2 to 4-fold and orders of magnitude faster than solitary robots. The goal is to complete a swarm testbed capable of competing in future NASA Swarmathon competition activities. And another goal is a testbed capable of training Tamushi CT students in swarm robotics, ROS programming, and multi-agent modeling. The background of this is from NASA and UNM, University of New Mexico. At UNM, behavior advanced foraging for food translated into adaptive search algorithms, which are then loaded into iAnt robots to search for resources. Foraging algorithms tailors those evolutionary tuned behaviors into error-tolerant, flexible, and scalable robotic foraging strategies. UNM partnered with NASA to apply these search algorithms to space exploration missions, which will require identification and retrieval of resources on the Moon, Mars, or other extraplanetary services.
So for our journals and patents, the two main patents that I would say have been very influential to us are the iAnt Swarm patent, which presented the information of swarm robots and related methods of how to operate a swarm. And the main difference between what we did and what they did is because ours is not related to Apple in any way. It also uses a different coding pattern. And the other one, which is the system methods for multiple place swarm foraging. This is an algorithm that details dynamic multi-place foraging. And it also is a very efficient algorithm for robotic swarms over unmapped areas like the competition will be. But ours, we are making our own ROS. We're not using this algorithm. This is just more of a instructional about what we would need to even begin making it. So for the proposed work, the project scope is hardware implementation, modeling of a foraging and collision avoidance control strategy for autonomous robotic swarms to collect resources on the surface of Mars. Now for the requirements and the constraints, simulation and physical hardware must be compatible to compete in future NASA Swarmathon competition activities. Our rovers must be fully assembled and operable. The robots must autonomously drive outdoors using GPS in the 5 meter square pattern. Swarm agents can coordinate and communicate with each other. They must be able to work independently of each other. Code uploaded of swarmies using search algorithms on their own without our input. We cannot input with them during the competition. And an efficient central place foraging operation that can be demonstrated autonomously. They have to be able to do all of this on their own. So for feasibility, economically, the project funds will be covered by the project sponsor, which ours is Dr. Rangel. The project funds will be more than enough to complete the project. The rovers or swarmies are manufacturable, sustainable, environmentally, ethically, socially, politically, and technically feasible. The project is relevant on many levels as it improves student knowledge, NASA's research, resource allocation, and critical thinking, as well as sparking curiosity in this field. All in.
Going into design standards, we've identified a number of standards here, two of which will be the standard for wireless LAN and medium access control, which is 802.11 from IEEE for Wi-Fi. And I'm sure everybody's familiar with the Universal Serial Bus specification, as well as a few that are going to be proposed for the IEEE. Here you see the concept map for our overall design. We'll have the Intel NUC, which will be the main computer, which will then talk to a microcontroller that will be parsing out the controls to the motors and the servo motors, as well as receiving the data from the ultrasonic sensors. Next slide. In the center here, you'll see the Lynx Motion chassis, which we've selected for this project. The top plate that was included with the chassis does not meet our requirements for the sensor mounting. So on the left-hand side, you've got a chassis top plate that will be utilizing an acrylic material for both strength and to prevent any sparks if we went with the aluminum material. On the right, you'll see the grippers and wrist plate, which we'll be using, which we've upgraded from acrylic to the 5052 aluminum per the sponsor's request. Here you'll see the control board that we'll be utilizing, which will distribute power both to the NUC as well as receive power from the batteries. It'll also receive the encoder information and the servo. It'll control the servos and the motors for the wheels. Here's our action plan. This is basically a summary of the steps that we've got for our project, which are outlined in more detail on the AON and the Gantt chart. Next slide.
For our network diagram, we decided to choose an activity on node or AON diagram. So you see start on the left side, finish on the right. We have paralleled any task that we can, and that is illustrated here. And then the legend for this diagram is the action plan that was shown in the previous slide, which also indicates the times between tasks. Here we have our work breakdown structure. So for our project, we split it into the rolling chassis, electronic components, the gripper arm assembly, and software. And then under each of those areas, it was then broken down again into various levels. We also created a linear responsibility chart. Similarly, it was broken into sub-projects, software, chassis, electronic components, and the gripper arm assembly. Those sub-projects were then divided into the tasks that were within them, and then one of our team members was assigned the responsibility for that task, as well as supporting roles level 1 and 2. And then if anybody needed to be notified or approved, that was also listed. For our resource leveling that's shown here in the resource overview, you see the blue indicates the work that is the actual work that has been done, and then the orange is the remaining work. It's not completely leveled among resources. We did as best we could, but this project, the heavy programming area really kind of differs in some of the requirements from each team member. So our resources for this project, we have our work resources, which is each of the team members, as well as our faculty mentor and our instructor. And then we also have the research teams at New Mexico State University and UCLA that are in charge of our coordination strategy, and then material resources, which are the robotic components.
For our tasks and timelines, as you can see on the left side, we have the initiation page, which has all been completed. We're working on the planning phase right now in this part of the semester. We've been reviewing 3D print, laser cut files, and as well as in parallel working on the software finalization with NetLogo, ROS, Apex, and Blender, as well as finalizing some last minute touches on the hardware. Moving on to the execution phase for next semester, we're planning ahead on procurement components, 3D printed components, making sure that we have our laser cut items, as well as the UGV assembly, which next semester we'll get the first rover rolling and then move on to the next assembly for the rest of the chassis, as well as the electronic components, which is very time consuming, but we have the required skills and materials to then go on to the testing phase. So for our implementation plan, we have our points of contact. On the right side, we have a table. We have our sponsor, professor, project manager, down to our mechanical assembly engineer. We have their emails and the contact methods, as well as the major tasks that they will be implementing. So on the right side, the bottom right, we have the tasks and milestones. So we're working hard to get these tasks completed in a timely manner, as well as our cost forecast on the left, bottom left. You have our labor, which is not just our resources, but as well as our materials. Then we have our test and evaluation plan. In our last competition, we will have to upload the simulation side before we can move on to the hardware. So that is a top priority to make sure that everything is running with the search algorithms, and then we can implement on the hardware. We have to make sure that both of them are running the same and making sure that we're hitting all their goals with picking up objects and making sure that our collision avoidance is optimal.
For risk management, we follow the 7 steps to risk management, starting with planning and then identification of risk, as well as the qualitative and quantitative risk analysis. And then we went on to plan a response for the risk, as well as monitoring and controlling, and the risk management database. Here we have our risk register. So you can see we have identified 6 risks. A delay in the robotic coordination strategy is our highest risk. You can see the probability and the impact of that one, as well as the category that it will affect. And then our response for that risk, since it is the greatest one, I'll go into some detail. We have to accept this risk because we are relying on computer science teams for this. So we will just manage that through meetings with them and our project sponsor. And then component price increase would be another one. You can see it has a moderate probability, but it will have a high impact on our budget if that were to happen. So our response for that would be to go ahead and find an alternative vendor. And then for our control plan, we will continue to review this risk register and then modify it as needed.
So for our monitoring and audit response, it'll be kind of combined since our team is small. We'll be conducting weekly meetings with our sponsor where we'll go over our schedule updates, our earned value analysis for time and cost, document lessons learned, review the risk register, and review the action items for the week and for the future. Since our capstone project is required, we don't have a termination plan. The expected budget, right now we're looking at $3,000 total from the project sponsor. The price per unit has increased from $850 to $1,000 due to computer upgrades requested by the sponsor. We will still be utilizing servo motors, which has reduced the unit price slightly. Right now we're targeting 2 complete units with the possibility of a third pending completion of the first 2 working. And then our in-kind expenses for labor is roughly a little over 51 Bitcoin.
Okay, you'll need to wrap up quickly.
Yes, ma'am. The earned value analysis here shows that we are behind schedule, but we're catching up to our baseline. Next slide.
For our accomplished remaining work, we have printed out the 3 components, finalized rover design, as well as doing some testing on Arduino. The remaining work is we have to finish the assembly of the gripper arm, as well as install the additional components and deal with any errors in the coding. So for conclusion, we will demonstrate a simulated autonomous robot mission in Martian environment. We will develop skills in ROS programming, as well as working with the Gazebo simulation engine and coordinating tasks on the Martian environment. Any questions?
Questions? Anyone? Dr. Rangel, do you have any questions?
No, actually, I'm very aware of the progress they've been working with. So I'm really proud of them. So they've been able to handle things. Right now, there's some little hiccups on the way because we ordered the incorrect part. So we're waiting just for that so they can start working and programming that thing. But I think based on documentation and the way they've been organizing things, they look that they're going into a good path. Just one comment with the slides, for example, in the background. I think that slide had too many words, so I don't recommend you reading from the slides to just have like the idea. I'm doing that presentation of what you know, right? So avoid reading the slides, just use them as a key point so the person who is looking at your presentation can follow you. But memorize or understand and make it a little bit less wordy, more like key points. But that'll be mainly the only observation.
Okay, very good.
Thank you, Dr.
Thank you. All right, I'm going to go back to slide 6.
This is our proposed working plan.
All right, so I see your requirements and constraints. I haven't seen your specifications, so that goes under your design criteria. Next, slide 7. Okay, again, this you need to back your statements up. If you're doing a feasibility analysis, this is your conclusion, but you need to provide some evidence for me to come to the same conclusion. So you need analysis of each of these components that you've listed here. Slide 8. This is an excellent slide. So of course you had to move pretty quickly on this based on the time constraints, but what you'll want to do when you list these in your report, explain why you chose these as relevant to your project. But excellent, this is exactly what I want to see from every project, finding the standards that are relevant to the design. Slide 10. So I see that this was modeled by Dr. Moses at UNM. So is this something you're making or you're purchasing or you're modifying?
So the chassis itself, we're purchasing the top plate and the grippers and the wrist plate, and that assembly we are laser cutting and using the CNC plasma machine to cut those.
So all right. So have you finalized all your design components at this time?
Except for everything except for our ultrasonic sensor mounts. Those have been. There's a little tweak there, but.
Okay, so remember that at this time I need to see all the designs in all its fine glory. So I need to see all the dimensions. I need to see all the specifications, which include the dimensions as well as the materials you're going to use them. So it's okay for the oral presentation, but for the report, you need as many details as you can give me, because remember, you're presenting your final design. Slide 13. Go ahead.
Just a quick question on that. As far as the dimensions and all that, do you prefer to have that in the appendix, or do you want that in the body of the proposal?
There's going to be body.
Okay, there's going to be like.
Well, okay, so include the ones that you think are important for me to understand your design. And then if you have additional ones, include them in the appendices, so that if I don't get to the appendices, I still capture what you're doing in the report. All right, so it is very important to make all slides self-independent. So you have plenty of space to include the key for A through X in this slide. So make sure that you do that. Slide 16. Okay, so I don't have a problem with the limited resource leveling. That's perfectly fine. I do have a problem with one member working 100 hours and the other member working 200 hours. That is a significant problem. If one of the members needs to work 200 hours, then you need to reconsider redistributing tasks to the member who's working only 100 hours. Everyone is getting the same grade, guys. So everybody needs to have relatively equal contribution to the project. I am okay with 10% discrepancy, but 100% is not acceptable. Well, 50%, depending on which one you take as your reference. Number 18. Again, this one is missing milestones. All the things that are listed on lines 35 through 38, because they do not require any resources, they are milestones. And I did not see any mentioning of design. So that really needs to be the bulk of your planning phase for this class. In actual industry, design is included in execution phase, but for us, we are just done with it in this class. 19, next one. Let's see what I had an issue with this one. Okay, so obviously in the execution phase next semester, you're building, you're testing, but you're improving and retesting and validating. So that design cycle needs to appear on your task and timeline. Slide 24.
Just,
Go ahead.
we've got a few of those. For instance, the line 45, we've got print a set of components, and then, 44, re-verify the models. So we've got.
Okay, very good, very good. Okay, great, great. Make sure you include, words like improve and retest, and
Okay.
you're fine. 24. Okay, so in order to do, did you include anything on monitoring and control? Did you talk about monitoring and control?
Yes.
It was kind of combined between the monitoring and control and the audit.
Okay, so for monitoring and control, you need to calculate the indices. So make sure you include that in your report. I need to see your earned value chart, which is next one. If you want to go to that one, we can talk over that one. All right, excellent. Planned value. Again, I only wanted you to draw 9 data points, and you did it for every single day, which is wonderful, no problem. And it's a monotonically increasing graph, all good. You have the actual cost, I believe, but you don't have the earned value chart. So earned value, one more time, it follows your planned value and it captures what you have completed and when. Okay, so let's say that on 8th of October, you planned. What is the vertical axis? You need the units on these. What's your...
Those are number of hours worked.
Okay, so let's say that for October 8th, you planned on completing, let's say 300 hours of work, but you only completed 200 hours worth of work, which means, well, I want to talk about the percent. So 200 hours worth of work should have gotten you, say, completion of task 1, 2, 3. And if you have completed those, then you have earned the value for those, okay? So I don't see an earned value. And we usually use cost on the vertical axis. There's no penalty for using this version, definitely. But in order to calculate those indices from the earned value chart, cost variance, time variance, schedule variance, as well as the cost performance index and what's the other one? Schedule performance index. You need a proper earned value chart. So you need a third graph that's up to today. But this is very good. I'm quite happy with this diagram. We like to see an S curve, but that's fine. All right. That's all I have. I really like this presentation. High energy, very fluent, confident. Everybody's dressed to kill. And you get it. I mean, you're communicating that. So just some fine tuning. Thank you very much.
Thank you, Dr. Ruby. Thank you, Dr.
All
Ruby.
right.
Thank you.
Next team, who's presenting, please?
It's me, Dr. Ruby. Sean, the bottom probably.
Okay, Sean, let me see you in my list so I can.
Oh,
If
sorry.
you talk, then you'll get to the top of
right
my
here, right
list. All right.
Sorry.
Okay, let's see if I can make you the presenter. Perfect.
See, I'm trying to share it.
All right. And I believe we're meeting after class today, correct?
Yes, ma'am.
Okay. Let's see, just give me 1 second. Can you go to, yeah, just 1 second.
Okay.
All right, I'm ready when you're ready, and your time starts when you start talking.
All right, well, my name is Sean Vela, and this is the Clamshell Characterization Project. My team members are Frank Monroe, Ulysses Sevilla, and Valerie Salazar. The project sponsor is Dr. Ruby. This is the outline of the presentation. We're going to follow this throughout the entire thing. All right, so our goal for this project is to create a tool that will compute the characteristics of a clamshell using three-dimensional scans. So the final deliverable is expected to successfully 3D model the clamshells and have the statistical results displayed on a mobile app. Down here at the bottom is our scope statement. So the scope statement is this project is for the creation of a clamshell characterization tool. The clamshell tool will use a 3D scanner to capture a 3D image of a clamshell, and the 3D scans will be uploaded to a development software to be 3D modeled and analyzed. The statistical analysis of the clamshell will then be interfaced into a mobile app for viewing. There's some background. Here at the top is the patent that's related to our project. It consisted of a real-time 3D computer vision processing engine for object recognition, reconstruction, and analysis. This project is similar to ours because both processes, we use 3D modeling to characterize an object. Down here at the bottom, we have the journal article. This is some of the previous work that was done. The work here consisted of a 3D scanner, the HP 3D Structure Light Scanner Pro S3 system, which used a turntable to rotate the irregular object in a 360-degree view, which allowed the scanner to capture every angle view of the image of the clamshell. I'm sorry. And then the 3D modeling techniques here, they were successfully developed. They characterize the shell's color, shape, size, and texture. And then in the work we'll be doing, we'll be characterizing the inner volume, outer volume, convex volume, surface area, peak shift, height, minor, and major axis.
Hello, my name is Frank, and this is our proposed work for the project. We are to scan and align all the shells to create a digital model. Use MATLAB to find the attributes and display those attributes to a mobile device like a cell phone or a tablet. The MATLAB script may also need to be modified or updated. For the HP scanner, the group will scan the remaining Solana and create accurate 3D representations to find the attributes. The process is quite lengthy due to the object size and being without obvious difference in physical features. However, with more practice with the alignment, I hope this process is set to be quicker as time goes on. For an accurate scan, the scanner needs to be calibrated to the size of the Solana. The Solana ranges in sizes, so a 30mm calibration might not fit larger shells, and a 60mm calibration will have to be used instead. On the left is the 30mm calibration used to scan the shell above, and on the right is the calibrated scanner view. And this is the Solana on the automatic turntable that I scanned, and the total number of scans taken for this particular specimen. So there are 27 photos taken with the quality of the scan that only improves if more photos are taken. So the group plans to scan the remaining 14 Solana with this process as well. And here's a completed model after fusing the scans together in the HP software. And on the right is an STL file, which can be viewed in MATLAB and any common software. Another app that seems more promising to quickly photograph the smaller Solana and create a 3D model is the Trinio app. The HP scanner is more powerful and can provide scans under artificial lighting for larger objects, while the Trinio app can automatically develop a 3D model for smaller Solana through an online service. However, the Trinio app struggles to capture a photo under artificial lighting and requires about 2 meters of space for the individual to orbit around the shell to take the photos. And here is a 3D model captured with the Trinio app service. And the last proposed work is to find the attributes of the 3D model in MATLAB. The script is provided by one of Dr. Ruby's assistants, and And the group may need to adjust that to fit the needs of the project as time goes on. And here is just some more lines of code provided to the group.
All right. The study of feasibility on a project is important when figuring out if the project is viable or not. The team took time and many considerations on trying to figure out the likeliness of this project. These are 4 important feasibilities the team considered: environmental, economic, technical, and social impact. The environmental feasibility of this project presents a benefic impact towards the environment. Being able to retrieve the shell's attributes and characterizations will eventually lead to environmental analyzation. The economic feasibility of the project also benefits the current economy by providing a tool that will be able to solve many problems marine biologists are having, that being the extensive process they undergo when retrieving the shell's attributes. And the team also expects to have sufficient funds to pursue the proposed design. For the technical feasibility of this project, the team has all the necessary technology and resources to accomplish the overall goal. Although there are some technical risk factors that we may encounter, such as file corruption and software incompatibility, but the team is well prepared to face these risks. The social impact of this project results in a positive impact. The development of this tool will not only have a good effect for marine biologists and scientists, but for anyone performing the 3D scanning of irregular shaped objects.
All right, so here are the standards and the design. Here on the left side, we have some of the standards. We have the software hardware interface standard. We have the tagged image file format standard. And then down here in the bottom is the for wireless computing network standard. And then here on the right side is the design. So it's the input as the clamshell, through the clamshell to output the physical attributes. Here on the left side is the design for when we're using the 3D scanning mobile app. And then, like I said, it goes to the computing, to the physical attributes through MATLAB, and out come the results on the mobile app. And this is our action plan. It starts from the beginning back in September, and it runs all the way through the end of April to the end of the presentation, final presentation. And this is the work breakdown structure. We'll use this work breakdown structure to successfully produce the deliverables. It should help our team with some organization. So here on the left, we have the scanning steps. Here in the left column, here's the scanning steps. And then we have the computation of attributes. And it just describes the steps necessary to convert files and then the modeling. And then here on the right is the data where we use for interface.
The linear responsibility chart outlines the various tasks associated with this project. As you can see, one team member has held responsible for each task, while the remaining team members are available for any help or assistance. Our mentor and sponsor, Dr. Ruby, is available to consult and improve certain tasks when necessary throughout the project path. All right, displayed is the activity on a node diagram for the project's plan. The diagram shows the beginning of the project as well as how each activity correlates with one another. The table to the right shows the letter key with the activities described.
All right, so this is the resource allocation. As of now, these are the number of hours each team member will work. These hours start from day one in September and end in the April. And the hours may change. It just depends on if there's any changes requested by our mentor, the availability of each resource, and any project dependencies. This is the task and timeline. We have from the initiation phase down to the planning phase. And then the second slide here, it breaks down the initiation phase. Initiation phase, and it has all the testing needs done, and then down here at the bottom, the termination phase.
Okay, so here's the implementation plan with the tasks, the schedule, and any notes that we might need for our project's lifecycle. And here's just a continuation of that. And there should be one more, I believe. There we go.
Displayed is the testing evaluation flowchart. The flowchart displays the testing and evaluation of the system. From the testing, it is expected to identify any errors or corrections if needed. This flowchart provides essential information for the parties invested in the project and also validates the performance capabilities and feasibility of approach to the final deliverable.
So this is our risk management steps we'll need to follow to account for any risk during the project. And then here are some notable risks the group may encounter and the possibility and impact of each identified risk has. And here is our budget summary. This is a list of materials that we'll need to complete the project. And here's a number of hours the group plans to finish the proposed work in the execution, testing, and termination phases taken from the project file.
The project's earned value analysis chart is based on the team member salaries of $20 an hour, the amount of work we anticipate the project will require, and the actual work that has been put into the project to date. A value of 0 was determined for the cost variance, a value of 1 for the cost performance index, which indicates that we are on budget as of now. A negative value is calculated for the scheduled variance, and a value of less than 1 for the scheduled performance index, which reveals a problem. For the monitoring and control plan, we must first perform the earned analysis, then calculate the variances and indices, and interpret the values to answer some questions that may arise, such as how did we get here and how can we fix this? Based on the results, the team is struggling to stay on track with the schedule. This doesn't mean we won't meet the deadline. It means that at this moment in time, we are behind schedule. After analyzing the results, we can determine the problem and identify the cause by noticing if the problem relates to the project scope, budget, or schedule. Finally, we can take control as a team and figure out the best way to fix the problem and prevent future occurrences. To ensure the success of a project, an audit may be conducted. This allows for the team to observe the current status of the project. As the project approaches the termination phase, the team must make sure that all tasks have been completed and the deliverable is finalized. The team will need to prepare a final presentation and report and return any borrowed materials. As at the conclusion of any project, it is a good idea to take time to reflect over the course of the project and identify how issues occurred throughout to prevent them from happening in the future. We have covered a lot, so just to recap, we will be using 2 methods to scan the shells, edit scans through the appropriate software depending on the scanning method used. The final scans will be converted to the appropriate file if necessary to upload into MATLAB under a specified account where the team will use codes to derive the shell characteristics. The deliverable will be the capability to display the results onto a smartphone using MATLAB Mobile, the MATLAB Mobile app, using the same MATLAB account. These are our references, and we are now open for questions.
Questions?
You're on mute, Ruby. Everybody's on mute.
Dr. B on mute.
You're muted, Dr. Ruby.
Oh, sorry about that. All right, I really like this presentation, much improved from last one. I have now a clearer path to the final prototype. By the way, I was saying this is for all teams. Each team needs to have a termination plan. Even if your project is completed successfully, you still have a termination plan. That means finding a home for your prototype, getting paid for your receipts, closing the books, etc. So this is for everyone. All right, any questions? Anyone? Okay, I have questions. I'm very glad to see that you managed to obtain your own 3D scans. That's a significant progress. Obviously, you need to work on improving those and close the holes, but we can discuss this after the meeting, after class today. As far as this presentation is concerned, you're on the right track, and I'm seeing progress. Slide 4. So when you are listing a patent, I'm okay with you including the cover page, but what you really need to include is a diagram if they have one. So
Yeah, they do.
yeah, so the picture is worth 1,000 words. So if you insert a picture, that'll help us understand what it is that you are, why it is that you are including this patent. Why is it related to your work? Okay, slide 15. I just wanted to say excellent work on the standards, and that's exactly what I want to see. The design again looks good. What is your final product? What is your final deliverable? So what is it that you're going to give to your client? In this case, myself.
So to have the characteristics of the clamshell on the mobile app, that's the final deliverable.
Yes, we plan to back up all these shells onto a digital file so they can be viewed without having to actually take them out of their storage.
Okay, so what if some new shells are scanned and they are uploaded to some cloud storage space, and I want to use the app to perform analysis? What do I do with that app?
Well, I think you would have to rescan the new shell.
Right. That's scanned.
Right.
Let's say that I've scanned new scans. How do I use the app to find the characteristics of the new shells? Okay, so that's the kind of stuff that you need to think about, because that's a useful product, right? That's where we're getting it. So, all right, but you're on the right track. I'm just thrilled to see the progress. Slide 21. Okay, so everything under, can you enlarge this for me?
Let's see.
If you can put it in full view.
Right there?
Thank you. Yes, that's perfect. So anything below line 16, 17, I don't see the timeline on the right-hand side is chopped off. Right?
Oh, yeah. Sorry about that. Yeah, I didn't even notice.
Figure out a way to include that information on here. Again, I don't see any milestones.
Yeah, I did. I noticed that after you were critiquing the other groups, I didn't include any milestones on mine.
Right, and then I need to see something about finalizing the design. I think what at the beginning, what was also missing is what is the problem? You described your project very well. I now know what it is that you're doing, but I still don't know what the problem is. Why are you doing this, right? So you want to start with that. That was a comment for slide 1 or 2. All right, so you need to make sure you capture the tasks that go under design, because that's the majority of the stuff that we've done so far.
Right, yeah, I left that out too.
Okay, slide. And again, this is team. You have 4 people on the team, so you need to distribute the tasks. Slide 28. All right, this is your risk management plan. Okay, this is your risk matrix, right? So I don't see risk management. This is, you need to go through those, at least the first 6 steps, and apply it to your project. And then you need to have a risk mitigation plan that comes from this. So I don't think I saw that. All right, next one, your EVA chart. So did you guys work exactly the same number of hours? So by the way, the EVA chart needs to be from quarter 1 all the way to quarter 4, if that's what you're using. So we have 4 quarters. 2 weeks, so quarter 3 is your fall? Is that what you did?
It's the end of the 2020 year. So
Okay, so you need
So
at
from
least
now,
9
yeah.
data points. Okay. Yeah, my comment was about the linearity of this chart, but I see why it's linear now because you only have 2 data points. You need
Okay,
at
so it
least
needs to-
9 data points, 1 for each month, September through May. Again, please fix this before you submit this, or make sure you fix it in the report. So that we can see that S curve. You know, you put very little hours like everybody else at the beginning because you're still figuring things out. And then things are now beginning to pick up, and next semester you're going to put a lot more hours into this. And that's where your slope, gets sharpens. And then towards the end, although most of the time my students put a lot more effort at the end, but the plan needs to follow the regular project life cycle. So, it's hard to interpret. So is your earned value then overlapping your planned value at this time? Is that why I don't see a blue graph on here?
the earned value is actually ended up being equal to the actual cost based on project.
Okay, so that means that you did not earn enough value compared to what you planned, right? So you should have a schedule variance, you should have cost variance, and you should have time variance, right?
I wasn't sure how to obtain the time variance through Microsoft.
Okay, so what you do is you take that green data point, that's the second one, and you follow it horizontally all the way to the left, and that gets you somewhere to the, somewhere along the same line. You hit red line, which means that this much work was supposed to be done. I don't know what your timeline is, but earlier. So you spend a little bit more time to get to that much work. So all right. We can talk about this after class. Okay. All right. That's it. Frank, I'm going to pick on you. You can't just say, here's our outline. Here's our, it's kind of insulting
sorry
to the
about
audience. Well, let me see if I can read this fast enough before they get to the next slide. Sharon, I missed it. So you really need to highlight at least the takeaways. I know you're pressed for time and I really appreciate you being conscious of it, but you really need to highlight the most important information on that slide at least. Okay?
Yes, ma'am.
All right, well done. I am very hopeful now, and we'll continue the discussion after the presentations today.
Yes, ma'am.
All right, thank you. Team number 4, who is presenting?
Mohammed Ahmed, Dr. Ruby.
Okay, let me make you the presenter. All right, give me 1 second. 20 seconds just to type things in. All right, your time starts when you start talking.
All right, can everybody hear me? Perfect. All right, hello everyone. Thank you for joining us. My name is Gary Sanchez, and I'm joined by my group members, Mohammed, Jacob, David, Hilario, and Jack. Also joining us today are our project advisors, Andre Guajardo, and of course, Dr. Ruby. Thank you both for joining us. This is our final proposal for our grocery carrying UAV. Next, please. Here we have the outline for our project. We'll mainly be focusing on the final design, the background introduction, our action plan, the work completed, remaining work, socioeconomic plan, and we're going to hopefully cover the earned value analysis chart. Alrighty. So today we continue to experience the COVID-19 pandemic, and one of the most highly recommended safety precautions our community must follow is social distancing. Many situations do not allow effective social distancing, such as grocery stores or food vendors. With that, our focus for this project will involve safely ensuring the delivery of a 10-pound bag of groceries at least 15 feet away, autonomously, and return to a home position in under 4 minutes. Ultimately, we hope to reduce contact between individuals, promote social distancing until the end of the pandemic, and as well as aid the elderly and the disabled. Next slide, please. Alrighty. So here we have the background of the patents we've been researching. The model designs that influenced our final design are owned by the companies Flirty and Amazon. Each company has their own unique way of packaging and delivering products, which we plan to improve upon. Although a couple of these UAVs can travel roughly 7 to 14 miles round trip, carrying only maybe about 5 pounds of product, our design will be able to travel slightly shorter distance and deliver twice the number of weighted products. All right, David.
Hello, my name is David. So the scope of this project is to design a UAV, identify the needed electrical components, design the software, and put everything together to meet the project requirements, which are the UAV needs to be controlled by a single user, and to carry a load of 10 pounds or more, it needs to be able to transport the load and drop the load at a distance no less than 15 feet, and do all of this within 4 minutes. Next slide, please. Feasibility. For technical specifications, UAVs are very common and are already proven to work. This project will only be adding onto those existing designs. For flight regulations, there's not really any FAA-related regulations since the altitude is really low. As far as the team capabilities, the team members have the skills and experience necessary to complete this project. Next slide, please. So our final design, it's a 4-rotor UAV with a 16-inch diameter propellers. The UAV will provide 30 pounds of thrust at only 80% throttle, giving us some headroom. The standards, for documentation, we will be using IEEE standards, Arduino language, which is a simplified form of C++ for the programming. And the last standards gives us guidelines for how to present units, quantities, and unit symbols for drawings and reports. Next slide, please. The UAV will be loaded and unloaded while it's at stations as shown in the figures to the right. The approach was chosen to reduce noise and provide more safety to both the person loading the groceries as well as the customer. And the grocery bag is not trying to scale. Yeah. Next up, please. Yeah. Here you can see different views with dimensions, and those dimensions are in inches. Next slide, please. And here's the UAV on the stand, just some more views. Next slide. This is how our General Electric flowchart is going to look like. And on the next slide, you can see that with actual components. Go to the next slide, please. And this is just a rough diagram with the actual components that we'll be using for this project. Up next is Jacob.
The expected deliverables for this project are designed tethered UAV that can autonomously deliver a 10-pound load within a 15-foot radius and then return back to the home position. This task must be completed within 4 minutes, and will also design the UAV to be compact and light enough to be portable enough to be fully operated by a single individual. Next slide. The expected resources are 6 group members, our advisor Andre Guajavo, and our advisor Professor Dr. Ruby. The expected budget for this project is $1,000. That's taken into consideration of $200 from the university. And each group member, along with Andre, have agreed to pitch in $100 each, so that's $700 right there. The hourly pay rate is an average of $25 an hour, and each group member has worked 15 hours. Next slide. Here is a components list. It shows the prices and quantities of each of the components we're planning on implementing into the UAV. Jack, you're up. Next slide.
Sorry for that. Okay, thank you, Jacob. Here we have our risk analysis, and again, we have it split into two different categories. This first being our technical risk identification, where you can see on our qualitative risk analysis chart, we have several high impact failures, such as a seized motor, battery failure, our electronic speed control failure. The reason we have so many high impact failures is because we're working with the UAV that if some of our control modules or physical components fail, it can be a really big safety hazard. So we have to worry about that more than we would with some other projects. Next slide, please. Here's our managerial risk analysis, where we used a SWOT analysis, analyzing our strengths, weaknesses, opportunities, and threats. Our threats, again, are going to be possibly going over budget, insufficient technical knowledge, or an insufficient amount of time. Our opportunities are high marketability. Next slide, please. Our risk response, for our threat planning, we're going to try to avoid going over budget by analyzing our purchasing options and comparing costs and specifications. We're going to spend time researching proper methods to complete the project in fields where we have a lack of expertise, such as programming. We're going to try to avoid technical pitfalls by examining existing patents, which we've already done, which has gone really well for us. Our opportunity planning, we're planning to capitalize on our high marketability to increase the chance of finding a sponsor. Unfortunately, that didn't work out, which is why we're funding the project on our own. But hopefully, whenever we present our project at the end of next semester, there will be some people that are interested in the design. For our risk monitoring and control, we're going to continue as a team to identify new risks of both technical and project management concerns, monitor our existing risk using our qualitative risk analysis as reference, with extreme caution regarding the high impact risk, which are legitimate safety concerns when working with the UAV. Next slide, please. Here's our task and timeline. This is the first part of it where we didn't make too many changes. I only shuffled a few things around and changed some dates with a few things we've already finished. Next slide, please. Here we fleshed out the assembly phase and testing phases a lot, and also used our new academic calendar, which has been updated a lot recently because of COVID, and changed some of those dates around as well. So we're just trying to adapt to all the changes that are happening at the moment. But you can see the larger assembly and testing phases. Alrighty. Next slide.
Okay, so the implementation plan we have is, since we are done with the final design, we have to just order the parts, do the software designing, and do the assembling. Okay, so it's just basically putting everything all together, testing, and then get done with the project. Next, this is the action plan we have. Then not much changes to it. It's just that the only thing that was added yesterday was the share of standards with our advisor. This is the work breakdown structure, which is divided into three components, which is the main body frame on the left hand side. You can see where we have to design, 3D print, and assemble. The middle part, you can see the electronics, which includes the speed controller, motors, main board, the battery, gyroscope, and the accelerometer. And on the right side, you can see the software part, where we have to design and program the software and test it. Over to you, Gary.
Alrighty, so this is our linear responsibility chart, which defines each group member's roles and responsibilities throughout the project plan. It's actually numbered for you at the bottom, so you can see who's actually responsible, what's going to be supervised, and who needs to be consulted for certain tasks. And next slide. Okay, Hilario.
So here we have the social economic impact, as we already talked about. It's going to be green energy. It's going to create new jobs on the manufacturing process if this idea works in the future. So also we're going to have the fast delivery from the app, a mobile. Just grab to the order online, and they are going to deliver to you in your car. It's going to be more efficient, and it's going to be less contact with this going on with the pandemic COVID-19. So it's gonna be stay safe for all the people. Over here we have the activity on node. This is an example of the earn value chart. It's gonna be up until 4 months. It's gonna have the start and the end, and it's gonna be give the budget of competition and earn the value, which include the hypothetical labor hours. Next slide. And over here we have the earn value chart, and it's gonna start like from month 3 and start going on. Next slide. On conclusion, this project, the main purpose is to help right now with this COVID pandemic situation and reduce the contact with the people. We are trying to do like the final design. We are hoping maybe to adjust some, have some adjustments in the future on, and the objective is to have the best weight carry UAV from all that they are already on. And the budget, we just work on the budget and start trying to find the cheap, to find good stuff with less money possible to stay on budget. Next slide. If you have any questions.
All right. Questions?
Sorry if I missed it, but what is your expected payload? Average payload?
10 pounds.
10 pounds.
All right. Did someone say 10 pounds?
Correct.
Yes, Dr.
Any other questions? Andre, do you have any questions?
No, ma'am. Thank you.
All right, let's go back to slide 4. But before that, I want to ask you, are you creating your UAV from scratch?
Yes, we are. It was a presentation. The bar is gonna be made of aluminum bar. We're just gonna 3D print like the housing for the electronics. And
Okay, but do you think since you haven't started yet, do you think you're going to have enough time to do it? Do you think maybe a strategy that uses an existing UAV and modifies it for your needs might be a better strategy?
we thought about that, but like the other choices, like a UAV that like met the requirements that we had, like for the loading, they were like really expensive as compared to just building our own. Like several times more expensive.
Are you planning on working during the break?
We haven't really talked about it, but I have no.
Well, let's go to your Gantt chart. Let's look at your Gantt chart. So the last class day is 24th of November, guys, and then we meet again in January 25. That's 2 months. And then you have February, March, and April. You have 3 months. This is for everyone, not just you, of course. So if you haven't had your hands on, it's going to take some time to order the parts. If you don't have your hands on the hardware yet, I'm a bit concerned about the timeline for this project. Okay, so I see that you updated the execution phase, so you're planning on starting on 25th. So can you go to the previous one? And this one ends today, so you're not planning on doing anything for 2.5 months?
Like I said,
Let me guarantee you, you will not finish your project. So you guys need to do some work or you won't finish. Okay? If you give a 2.5 month break, it's not going to happen. All right, slide 4. All right, I like this. Make sure, you include the title of the patent so we know what it is, but all the information is there. And I appreciate that because remember that all slides need to be independently informative because we may, if someone's audio goes out, at least they can read what's on your slide. So I know that in the past, this is for everyone. In the past, we were told to keep the slides to the bare minimum. You're there to explain things. That is still correct. You don't want too crowded slides. However, the slides should be informative and not just an outline for you, because if the audio goes out, then the audience should still get information from your slide, okay? All right, this is for everyone, not for you guys. All right, slide 6. And by the way, you explained the problem really well at the beginning. So now, you mentioned COVID situation. Now everybody's intent. They understand the problem, and now we're curious about what you're going to do to solve it. So that was a very good transition. Again, you identified the feasibility points very well, and you verbally explained them, but you need to introduce a little bit more evidence about why this is feasible, okay? So we should not have to take your word for it. We should be able to see some evidence that this is feasible and then come to the same conclusion as you're coming. All right, slide 7. Is this your design?
Yes, this will be our final design.
Okay, so where's the motor going to go to?
So the motor's right below the propeller.
Under, okay. And then the white housing that's going to hold the electronics then?
Yes.
Okay, what materials are you going to use?
For the frame, it's gonna be aluminum bar, 1-inch aluminum
Okay.
bar. And for the housing to house the electronics, the white thing, is gonna be 3D printed.
Okay, and I like the cage that you're using for the propeller, but we probably need to make sure that it is all the way around and not just
Yeah, right now.
halfway if somebody,
Yeah, right now I have it set to only 140 degrees, but I did thought about increasing that. So that's something we'll be doing.
All right. Again, standards, we're making progress. You've identified the ones that are relevant to your project, so that's great. And then the ISO standard, that's a very specific one, so that's very good. But for the IEEE and Arduino, you need to find the code that goes with it. Obviously, IEEE, we have access to it through the IEEE Explore database. We may not have access to some other ones, but you should have access, or you should be able to find at least the title of the standard, even if you don't have access to it. So that's all I'm asking at this time, okay? All right, slide 8. So obviously you need to, use a software tool to show the dimensions. And I tend to think that you will need some sort of a table and a flat top, because it'll be very difficult to make sure that when the UAV comes back, it can balance itself on these two narrow beams, right? We're looking for trouble there. So make sure that you put a flat surface on those two stands so that the UAV can just easily come back home. All right. Okay, and we need more dimensions, of course, because you're presenting this as your final design. So since you're, the MET folks need to show exploded views, different diagrams, different CAD designs. That's your design. So I need more details. Slide 9. All right. Yep, that's the dimensions there. Again, you need to find a better way to cage the propellers for safety purposes, since it will be available in public. And slide 14. So the group has completed 15 hours work. Is that for the entire semester? Is that cumulative? Or is it 15 hours per person? All right, your silence tells me a lot. So I am very concerned about the progress of this project. We really need to get it moving because what you're proposing is it's got a lot of moving parts. So it's going to have a lot of troubleshooting needs when you start building it. And I'm concerned that we'll be pressed for time. And if we go fully online in January, that's even more problematic because you won't have access to the workshop and you'll need to figure out how to get this done outside. So I highly recommend that you use your time wisely to make progress. All right, I have slide 19. Okay, by the way, I really like your risk management plan. Very well done, very thoroughly addressed. This one, I believe I wanted to see more details about the design.
Yeah,
And it's not just journal and patent applications. I mean, this should be a bulk of your TASM timeline because that's what we're doing right now. So you need to add meaningful details of tasks and durations as well as milestones. I don't see any milestones on your chart. And then
we only have a couple.
yeah. Okay. 23. I like this, and actually I was going to ask if you were building it, and that you just told me that, so I have the answer for that one. 24. Okay, so remember we discussed this before. We said that the electricity company will not allow you to put more than one person on the electric bill. And the reason is if that bill does not get paid, they want to know who to go after. Okay, so if you have a task which has more than one person in charge or actually responsible, we have a problem. If that task doesn't get done, then we don't know who to go to ask questions. So you can only have one person assigned as number one responsibility in the responsibility chart. So in the weekly meetings, the project manager can be the person responsible for arranging the meetings, and everyone else may be, notified when the meetings are, but you can only have one person who is responsible for each task. So what that means is you need to separate your actions in such a way that reflects the tasks that each person owns. Because I understand that most of these tasks are team tasks, but then you cannot allocate who is responsible. So you may want to revisit that. Slide 25. I really like this chart. I think you hit it right on the spot. We understand the socioeconomic impact of the project, so this is very nicely done. And that's all I have. Again, I think you have a very interesting project. There's a high interest in this project. This project was initiated by the community, so it's very important for us. So we really want to see it succeed. And you have 6 people. You have a lot of human resources on the team. You have Andre, who's an expert electrical engineer. Use his time, use his expertise. But you guys need to plan to work in the next 2.5 months, because otherwise it won't get done. All right, good presentation. Thank you. And Andre, thank you for logging in. Next team, who is presenting?
It's going to be the Volkswagen body team.
All right, I meant who needs to be the presenter.
Oh, I'll be the presenter.
All right.
Hang on, I'm having troubles with my video.
I'm very happy to report that everybody's dressed up for this presentation, so nobody lost any professionalism points except for one person whose video was not on. So make sure you turn your video on.
Is it on now?
Who's talking?
Me, Jesse.
Okay, yes, we can see you.
Okay, good. Yeah, I wasn't turned on for a second.
All right, and your time starts when you start talking.
I will begin.
Good afternoon, everybody. My name is Kyle Carter, and today my colleagues and myself will be sharing our updated design plan for our capstone project, creating an aerodynamic body frame for a VW Super B. Next slide, please. Our outline shows the breakdown of our presentation from our design ideas, our projected budget, and our projected plan, ending with our risk analysis and our dependencies. Next slide, please. The objective of our project is to The objective of the project is to create an aerodynamic body for a VW Super B floor plan. We'll be constructing this body frame from scratch, making critical decisions based off of how much material will be used to make a sturdy body that is safe for the driver, fuel efficient, and compliant with national and state regulations. Next slide, please. We've taken some ideas from relevant research to use as reference when moving forward in the development of the frame. For instance, a study in the World Electric Vehicle Journal analyzes the correlations between electric vehicle design and standards versus their performance. Most relevant in that article is that there is found to be a clear correlation between vehicle weight and its overall fuel efficiency. We'll go more into that later in the presentation. The group has also considered the inclusion of wingtips onto the exterior body to reduce drag. These wingtips have been proved to show a 5 to 6% increase in fuel efficiency when included on aerodynamic designs like airplanes and cars. Next slide, please. The project team has been using a 3D modeling program to design both the internal and external body frame. Starting in January, the team will begin assembling the interior roll cage that will house the passenger, as well as beginning construction of an external aerodynamic body. Using our 3D modeling software, the team has already substantially stress tested our design roll cage against external stresses. And the team has also begun stress testing samples of S-type fiberglass and resin mixtures, which we've labeled, going in different. We've also begun testing samples of S-type fiberglass and resin mixtures and layers, as well as alternate weaves. The samples that prove to be the most efficient will be applied to our final body, external body frame design. To go into more depth, I would now like to hand this presentation off to Jesse Wilson and my other project mates, who combined have years of experience in the automotive industry.
Hi, I'm Jesse. For feasibility, the aerodynamic body will improve power consumed by the electric motor. Also, electric vehicles will help reduce greenhouse gases emitted to the atmosphere. Also, our material used will prevent corrosion and other weathering towards our vehicle's body. The team will also help perform multiple analysis and provide critical data to our project. Next slide, please. The external body, the 3D model represents a finalized design constructed from epoxy resin and S-type fiberglass. With an optimal teardrop and an aerofoiled shape, which will yield to a lower drag coefficient. If you haven't noticed already, drag is forces acting in opposite direction with respect of the object surrounding fluid. Next slide, please. For the external roll cage, which is shown with the Volkswagen Type 1 floor plan with a lower subframe constructed with 1.5-inch square tubing, the roll cage will help protect the driver from sudden collisions and other accidents, which will also help support the fiberglass pieces during construction. And the roll cage will be constructed with 1.5-inch, quarter-inch thick chromoly pipe, which will be mounted, most likely welded to our lower subframe, which will then be mounted onto our Type 1 floor pan. Next slide, please. And this image is our block diagram. It simply demonstrates how the vehicle will be sub-assembled in pieces for ease of construction. The windshield and the floor pan is highlighted in red because these are our critical parts which will provide the proper scale for our project. And then the red hash lines will be the cutouts for our doors and driver and passenger window. I'm going to hand this off to our next presenter.
For our work breakdown structure, we have decided on how we're going to actually form the mold. It's going to be in 3 pieces. Using those 3 pieces, they'll be broken down and cut up as the doors, the trunk and hood pieces, and then assembled together as shown in the breakdown structure. Next slide, please. For our LRC, from the last time we presented, there has not been any changes due to this. Next slide, please. However, for our Gantt chart, we overhauled it, fixing a bunch of issues that we had with how tasks were laid out and their duration that they were taking up. This has drastically improved how much the project will cost, dropping it roughly $100,000 in price. And next slide, please. For our implementation, everything has been planned out to start off at the end of this semester. Some of us will be working on getting some of the molds and stuff done before the start of the capstone semester. And I would like to hand off to Lewis now for slide 14.
My name is Luis Galvan, and I'll be talking about risk analysis. This figure shows the risk assessment cycle, and it's a breakdown of how our team plans to create, review, and finalize a plan for our potential risks. Next slide. Our Volkswagen Super Bee will be constructed out of fiberglass, and this composite material tends to break or crack upon impact, as seen in the jet ski figure below. But it is also known to be very lightweight and cost effective. Next slide, please. Risk assessment sheet and risk matrix. Our team formed a risk assessment sheet to identify the possible risks throughout the project, along with identifying their likelihood and severity, and the remedial actions that will need to be taken to avoid these risks from occurring. Then these risks were placed into the risk matrix table based on their likelihood and severity. Next slide, please. The figure for monitoring and control plan shows the inputs such as our project plan, project documents, and work performance, which then leads to our team judgment based on the data analysis and standards we need to follow throughout the project. And then the figure concludes with us updating our project plan and documents based on our team decision making. Next slide.
All right, so I'm Zachary Lamandola, and this is the audit response. We have the audit response chart on the right-hand side, and of course, this is to show the true status of our work performed during our project, and it's broken down into categories of strengths, weaknesses, opportunities, and threats, and of course, this is for improvement of risk identification. Next slide, please. So the standards and safety precautions to follow have to meet national safety and equipment laws and regulations, and it must comply with the inspection of the requirements of the motor vehicles as well as the emission standards. And the correct PPE is needed for the fiberglass, the resin, and making of the roll cages. Next slide, please. For the state regulations and requirements, the biggest one that we added onto this is the protection of front seat occupants with this code. So our aerodynamic body needs to be resistant enough and strong enough to protect the passengers on the front side, and also there's the roof crush resistance. So it has to be able to withstand some force from above. And the title will also be considered a replica car for the Texas Transportation Code. Next slide, please. So for the laying of the fiberglass, this diagram shows the particular steps, and it's also, this is found from the Western System Handbook. And then I'd like to present the resources and materials with my other classmate, to my other classmate.
Hello, I'm Ben. I'm going to be talking about some of the resource materials and concluding this presentation. As can be seen here, we have some raw materials, the fiberglass and epoxy, parts that we'll be purchasing on order will be the windshield, floor plan, seats, and then some support materials such as cups, papers, and brushes. So here we have the startup capital of $3,000, and we have a grant from the TMCC of $300. Here on the budget sheet, we put a contingency of 15% for any unknown costs, as well as we estimated materials purchase, which is $800, and that leaves us a remaining balance of $95. Here is the earned value analysis chart. As can be seen, we have the actual cost in blue, and in orange is earned value and planned value, and then finally at the top is the budget at completion. We have another chart here, which is the project evaluation of the $3,300, and this is the estimated costs over the time of the project. So here we have the AON diagram, and the bold arrows are the critical activities, and the table to the right bottom is the early start, early finish, late start, late finish, and the duration of each activities. We also have relative projects to work with, which is the pneumatic transmission and the 60 horsepower electric motor, which will collaborate to make the body of the vehicle. And finally, we hope to have the project actually finished in the spring of 2020. We also plan on doing work over the break and finishing the roll cage and finishing our samples. And then overall, we hope to finish the comfortable vehicle and body that Mr. Carlson approves of. Any questions?
Sorry, is Mr. Carlson here? Did you invite Mr. Carlson?
We did, but I don't think he showed up today. I'm not sure if he's here.
Sure. No problem. All right, any questions from the audience? Everything crystal clear? All right, I have some questions, obviously. All right, let's start with slide 2. So you have explained the scope of your project and what you're going to do really, really well. Actually, I meant slide 3. However, you didn't start with the problem. What's the problem, right? So you have a client who is converting who's redesigning a vehicle, electric vehicle, in the form of VW, right? And so you need to explain the problem so that what it is that you're doing kind of goes in context with that. Really minor, just 1 or 2 sentences and you're done. All right, obviously you got these designs from somewhere. You need to make sure that they are referenced in the slide. So unlike reports where we put in parentheses or square brackets number 1 and then we put the detailed reference at the end, in visual presentations, remember that each slide needs to be independently informative. Therefore, the appropriate reference information needs to come in here. So I'm assuming this is from Volkswagen Corporation, right? So there should be some reference to it. So just include that on the slide itself.
Okay.
All right, and slide number 4. So same thing here. Is this one of the patents, I believe?
Yes, that
Right,
was
so
on
you
one of
need
the
to
patents.
clearly, yeah, right. So you need to clearly label them as patent with patent number, inventor name, the title of the patent, and the year the patent was awarded. That needs to be on the slide, okay? Unlike the report, in the report you can say figurative blended winglet patent and then put number 2 and then list all that information, the references, but in slides we have to put everything on the slide. All right, next one. Number 5. I really like this slide. It already shows some preliminary work that you're using that goes with your technical feasibility. Okay, so this is the kind of proof I'd like to see when you present your feasibility analysis. It's feasible because these are the expected type of forces that will act on this, and based on the materials we're using, this will hold, or whatever the language might be in your field. But this is the kind of evidence that I've been talking about for feasibility analysis. Now, you said that this will be welded. Usually the weld points are the weakest points in any design. How are you going to ensure the strength of weld to withstand an impact? I had a frame made for my optics in my lab, and then somebody hit it with their elbow, my mistake, and everything came crumbling down.
Right, I understand. I'm not an expert on welding. I believe that one of my teammates is, so I'd like to redirect it to my teammates.
Sure.
So for the welds, I mean, we haven't really gone into depth for analysis for the welds, which is, I'm glad you brought that up. So now we can also look at that as well. I would assume that if we need some other critical points, we can reinforce some of those points or those critical points for our roll cage.
Okay, slide 6. Again, so same thing, just make sure you insert some evidence to convince the reader that all these things are feasible. Slide 8. Slide 8 was about the welding strength. You already answered that one. Let's keep going if you don't mind just running through these slides real quick. Good, keep going. I was unable to read your Gantt chart. So consider breaking it down to 2 because it's jam-packed and I just can't read it.
Actually, on one slide and then that timeline on the other one.
All right, so this is true in general when you're giving oral presentations. If you can't read it, don't put it because it's just a pretty visual right now without giving us much information, okay? All right, let's keep going. All right, very good. Next one. I really like this chart. It shows us the loop, the cycle. Next, I have slide 19.
This one?
Oh, can you go back to the monitoring?
Oh, this one.
Okay, thank you. So monitoring and control requires that you calculate the variances and indices from the earned value analysis chart. Okay, so that's why we're calculating cost variance, schedule variance, time variance, and performance indices. So it needs to be incorporated into your monitoring plan because those are the numbers that tells us if something is behind schedule. Okay, for the purposes of project management. Now, for the purposes of technical accomplishments, this is okay. For the purposes of figuring out where the project is, you need the indices, and that's what I expected to see in this slide. All right, number 19. So you mentioned some of the standards that's applicable here, I believe, but you didn't specify any. The next slide is really good. You identified specific codes, so that should be that should satisfy our standards and codes requirement for design when we move forward. Okay, slide 21. So can you go over this slide? This is not your design, correct?
No, this is in the technical manual of the OSHA. You can find it online. Is that open
Yes, so you need the full citation on this slide. Because otherwise, you misrepresent yourself in the sense that people will think that this is your design and it's not. And then if you have identified the standards, then there should be a code associated with it. Section 5D, there should be something specific. So, I mean, you got it, you found it, just cite it, and then you're done. Okay? And then 28.
28, you said?
Mm-hmm.
The conclusion?
Yeah, I don't know why I said 28. Can you go back to the EVA chart?
Yes.
So why do you have 4 of these graphs?
This is what we pulled from the Gantt chart, and this is I kind of looked in the book, and this is what we had done in the book.
Okay, so your planned value is the one that actually goes from day 0 to April 30th, so September 1st to April 30th. That's the gray one. And then what was your yellow one? What is BAC?
Budget at completion.
Okay, so that's actually your planned value,
Yes.
right? Or is that your predicted value based on the current trend?
Right, it's a predicted value.
Okay, so your gray one also needs to go all the way to the end. And then earned value and actual value is exactly where it needs to be. So based on this graph, is it correct to interpret it such that you may be slightly behind schedule?
Yes, we are slightly behind.
Okay, there's no penalty for that. So that you've noticed that by monitoring it, right? So these are where you get all those indices, and it tells you that you need to have some control now. You need to have intervention. So what are you going to do to get back on track?
We were going to have to work over the Christmas break.
Okay. Also, one more thing, the cost on the left side, does that include your personnel hours? I don't think so. Does it?
I believe it does.
Because that looks awfully low if it includes the personnel hours. So you may want to revisit that also.
We recently redid the Gantt chart, and by redoing it, we cut down the cost by about $100,000.
Okay, but you have 6 people on the team, and how much are you paying everyone per hour?
18 an hour.
How many?
18 an hour.
15. Okay, all right. Just make sure that you're putting enough hours into it, and the low value may be that because you're not paying yourselves that much. All right, I'm satisfied. Good work. On the right track, it has all the components that I was looking for this presentation. Make sure that you have explanatory text in the report. Thank you.
Thank you. Thank you.
All right. Team number 6, who's presenting?
If you could share with Blake Brown.
All right, one more time. Who was speaking? I'm sorry, I didn't catch that person.
Blake Brown.
Okay, I see you, Blake.
All right, let's see here. Can everybody see my screen?
Yes, if you can put it into presentation mode, that would be great. Perfect. And your time starts when you start talking.
All right, good afternoon. Today, my group and I will be presenting our capstone project of our pneumatic shifting mechanism. Presenting today will be myself, Blake, Kyle, Justin, Christian, Eric, and Jaron. We'd like to thank Dr. Ruby for all of her help through this time, as well as Mr. Carlson. This is going to be our outline for our presentation today. A few of the key subjects that we'll be speaking about are going to be feasibility, design, our expected budget, as well as resource allocation and accomplished work. Introduction and design objective are going to be our problem statement, which is the vehicle needs to shift using a pneumatic system. Some of the motivations that we have are going to be converting a gas engine into one that completely runs off of electricity. Some of our design objectives are going to be a mechanism that responds as well as shifting goes and stuff like that. Responsible for clutch engagement between upshifts and downshifts, able to shift into neutral whenever desired, as well as reverse gear is not needed. Some of our background, this is a patent that we looked at, and what it's over is a method for a shifting system. The way it's similar to between our design compared to theirs is it's a manual transmission for a vehicle. It has a similar format to what we're looking for, as well as less human input. Some of the differences are ours is going to be pneumatic shifting from first to fourth gear, as well as smoother transitions and more detailed steps.
So for our proposed work, we have our scope, and our scope is that we want to produce the shifter for at or under the budget. And we also want to meet any safety requirements that's going to be outlined in our standards. Safety is our number one priority, and when dealing with an automobile, it is very important to put safety first, because it's the driver's life and whoever else is on the road with them. And any requirements or constraints we have a very small amount of located space underneath or next to the transmission that this is going to be fit into. It has to, the Arduino and the circuitry has to operate on the batteries that are provided. It can't jump gears, so it can't skip from first to fourth or from fourth to first, which would be very bad. And it has to shift at a push of a button. Next slide, please. So for technical feasibility, our materials and labor is a big part of our feasibility. So our budget is $2,200. This budget is going to cover any materials we have to purchase. Our hours worked are not going to be, we're not actually going to be paid for our work, unfortunately. But if we were in the real world, we will also count, our hours worked, so that way we can get an understanding of what a project like this might cost. Any logistics we have. So we have all of our group members, any expertise that we bring to the table. Also, Dr. Carlson's expertise. We have the engineering shop for now. We have discussed that if we may go online or the school may get closed down, we have 2 other shops we can work with. We have trailers to move all the equipment. So with the pandemic, if it gets worse, we are capable of moving this project. Technology, we have Arduinos, we have circuitry, we have the capability of getting all the products that we need in a timely manner to make this project work. Next slide, please.
So this is the mechanical design, just drawn in AutoCAD. And you can see the at the top measurement, it's 14 3/4 inches. And we think we can probably get that down to probably somewhere around 13 inches, maybe like 12.5 at the least. It's because we don't know exactly where the outlet is on the air tank. So if that's in a decent place, we should be able to move the solenoids over to the right some, as well as get the compressor and air tank much closer together. You can see all the cylinders and the manifold and solenoids and all the parts that go into it on that one. Next slide.
So for the electrical design, I've designed an opto-isolated circuit with MOSFETs to control the solenoids, and the solenoids are double action. So this circuit will actually be doubled in size, because each one of the solenoids has 2 actions, and this is only for 1 action. So this needs some expansion, but this is more or less the design. Next slide.
So here we have our action plan. The first of which is going to be to code the Arduino, and that's going to be Christian's responsibility as the team's electrical engineer. And the next we have auditing the previous work, should be by Blake Brown, using Mr. Carlson as a resource, just to see what the other team has done that we can use, and anything that might be changed. Like I think the previous team was using stepper motors instead of pneumatics to actuate the transmission. So obviously that'll get changed. And so working all that stuff out with Mr. Carlson and our team as a whole. And then next we have designing the electrical system, which is Christian again as the electrical engineer, which he just went through. Checking with the aerodynamic body team who presented before us for any constraints. We're going to have our shifting mechanisms going to sit above the transmission. And so that's going to have to be accounted for in a transmission tunnel in the floor plan of the body. So just checking with them for constraints, and the next actually meeting with them to resolve any conflicts, such as what I mentioned before. And we've got Eric as responsible for those. And then we'll be ordering and obtaining materials and parts, which we're ready to do. And so that kind of includes receiving the parts and going through them as well, making sure we got what we ordered. Justin's going to be on that. And then next we have designing the mounting brackets for mechanical components. That's going to be my responsibility. And so we're going to get the parts in. Obviously, you see Z is a prerequisite to that, which is ordering and obtaining the materials and parts, just so we can make sure everything works together and everything's as it's said it would be in the design and from where we ordered it from. Next slide.
Here we have our accomplished and remaining work for the project. The left graph shows our work status for all work resources. It is split up, showing total hours it takes to complete the project versus the assigned group members to perform the work. As you can see in the middle of the graph, it shows Christian as having more hours of actual work versus his remaining work. And this is because of the training he will need to learn to code the Arduino. The graphs on the right show the percentage of work status done by all the work resources. These graphs and tables help the team in being able to assign and make a smooth transitions of the overall workload of the project. Next slide.
So this is our work breakdown structure for the project. So the shifter is divided into three pieces. We have a pneumatic system, an electronic system, and a bracket system. The bracket system will be designed by Kyle and Jaren, I believe. I'm responsible for the electronics, making sure it all works. And then the pneumatics, they're going to take care of that. But each one of those has parts and pieces that make it whole. Next slide.
So this is our LRC. Thank you, Christian, for continuing on. So it's similar to the last LRC that you saw. The implementation phase shows more independent work compared to the planning phase that we were dealing with this semester. Hopefully for next semester, we'll be splitting off into smaller sub-teams in order to continue working in parallel. Next slide, please. Thank you.
In this slide group, we created an activity on node diagram for this semester's activities. The start and finish node are depicted by the ovals and are milestones. The rectangular boxes depict the activities to be accomplished over the semester. The arrowheads show the direction of precedence. For each activity box, the group determined the start dates as well as the end dates and duration. Next slide, please.
This is just a breakdown of what resources we've been using. We've talked to Mr. Carlson multiple times, and to try to get a idea of what he thinks we should do and kind of a direction that we should go in and make sure we're keeping up with everything that he thinks we should. And we're going to be using the workshop to build the brackets and to assemble all of the parts. We're probably going to have to use a couple small pieces of aluminum from the shop to make the little brackets to hold the actual cylinders. We're going to be using, obviously, the 4-speed manual transmission from the Bug and the Arduino board to tell this thing when to shift and stuff, and battery to power the compressor and the Arduino. And we're going to keep track of the budget, obviously, to make sure we don't go over, which we shouldn't even get close, but you never know. And we've been using AutoCAD as well to design and kind of get a basis of where we should locate stuff and easiest way to make it as compact as possible.
So for our tasks for the fall, we just had an informal meeting with Mr. Carlson this week where we discussed some new stuff that maybe we could add onto the design involving purging the tank with from water and water air separators to be added in between the tank and the solenoids. You can see right there, task K is the main one that influences our accomplished and remaining work. Found in slide 10, that task that runs in parallel with the rest of the thing is, with the rest of the project, is really throws a lot of hours, or it looks like it throws a lot of hours Christian's way. And we can see tasks W and X were sort of put back because of the informal meeting we had. No fault to Mr. Carlson. It just shows that we're slightly behind schedule, but we're really not. Next slide, please. So as we move out of the planning phase into the implementation phase, we'll get our parts ordered. There's about 13 days between tasks A, D, and AH dedicated specifically to testing and evaluating the design and tuning it, as a matter of fact. And then there's also a few days of slack after that in case anything goes wrong and we need to actually go ahead and revisit the testing and tuning. Next slide, please. Here we can see the key for the tasks. I couldn't fit it on the other two slides, but you can see task K, where it's learning the code of the Arduino, W, X, editing bill of materials and writing the report, which has already been started, A and D and A and H, function testing, tuning pneumatic and electrical systems, all these that were mentioned in the prior Gantt charts. Next slide, please.
So this is our implementation plan. All the parts ordered prior to the spring semester, or all the parts will be ordered prior to the spring semester, just so that when we start spring and begin construction, we have everything we need to go to move forward, and we're not waiting for anything else to come in, just in case something has to come from overseas or anything like that, or any sort of COVID-related delays in shipping. We just want to be prepared for all that. And then before we get, the first part of construction is going to be fabricating the bracket that'll hold or brackets, plural, I should say, that are going to hold the pneumatic cylinders, and of course the electronics box too. And then anything else that's going to hold, the lines and stuff like that together. And then the electronic and pneumatic teams are going to collaborate in parallel. So Christian with all his electrical designs, and then the rest of us, the mechanical, and we're going to help Christian out as well. But the mechanical guys and the electrical engineer, Christian, we're all going to work together and make sure that it all works smoothly. And then we're going to assemble all three systems and test and troubleshoot from there, just to make sure everything works as it's supposed to. Next slide, please. And as far as testing and evaluating, after we've constructed everything, the parts are going to be tested for their functionality individually, just to make sure we didn't get
You guys need to wrap up.
just to make sure we didn't get anything that was dead on arrival, and then we'll test everything all together and make sure it works, together. Next slide.
This is the risk management plan and the risk management matrix, and we plan on avoiding most of these risks by ordering commercial grade parts, fittings, solenoids, and cylinders, and we're going to use nylon hose, which should prevent us from getting any kind of air leaks. Next.
So our standards for monitoring controls and whatever, we're going to have weekly meetings. We're going to keep our risks low by having these meetings. We're going to order and correct commercial grade parts. We're going to keep an accurate record of our budget, so that way we know how much money we have left. We're going to follow IEEE standards for the transmission, along with any Arduino standards that may apply. And we're going to follow the standards listed for air tanks and pressure regulation.
So for our audit sponsor, we'll be auditing our performance, budget, schedule, Mr. Carlson and Dr. Ruby's satisfaction, our own teamwork and ethics, and the current status and performance of the project bi-weekly during the construction phase, just to make sure everything's working as it should. And the project's going to be terminated by integration into the remaining projects that consist of the electric vehicle. So Mr. Carlson's kind of obviously been dividing up different parts of this electric vehicle for different capstone projects. So our project will get completed and then go on the vehicle, and then we'll make sure there's any resources like instructions or schematics, so that if any other team has to modify anything or just understand better how something that we designed works.
We need to wrap up.
Next slide.
All right, so this is an updated budget. We swapped one of the solenoids from a single acting to a double acting, which is a little more expensive, but it'll make the clutch actuate much better. We had to add a couple gaskets for the fittings and a couple more different fittings in order to make it work better. We also swapped from buying the compressor and the tank separately into a tank compressor combo, which ended up being about $50 cheaper. Next.
So here we have our earned value analysis chart. The schedule variance of the project is practically zero, with both the estimated actual cost and cumulative cost of completing tasks overlapping or slightly under the EAC at the end. The time variance of the project is 1 month, with both the estimated actual cost and the cumulative cost of completed tasks overlapping or slightly under the EAC at the end. The cost variance of the project comes out to $7,324.80 due to the cost variance being assessed at the beginning of the month rather than the end, where the actual cost would have risen to make up for this difference. Next slide.
You guys are at 17 minutes, so I'm going to stop you there if you want to say what your conclusions are at this time.
Okay, so in conclusion, our overall goal is to implement a pneumatic shifting system to shift the VW H-pattern transmission that will be driven by an electric motor. We will use our risk analysis will be implemented to help determine important tasks to focus on, and finally, all the tasks need to be completed in a timely manner in order to meet the deadline of the project.
All right.
That will conclude our presentation.
Thank you. And in the interest of time, I'm just going to dive into the questions real quick. Slide 5. Please don't leave yet because we have 20 minutes of lecture to do. This lab goes until 4 p.m. All right, so again, your scope is to do with performance. It has nothing to do with budget. That's just your project goal is to be under budget, to be on time, and to be within scope. So please rephrase your scope number 1. Also, which ones are requirements and which ones are constraints in that list? To fit it in allocated space, is that a requirement or a constraint?
That's a constraint.
That's a constraint, right? Because your design needs to be within the realm of those space limitations. Operate on the batteries provided. What about those?
That's more of a requirement.
That's
I would
also
say
a constraint, right? Because it needs to work with the given batteries and nothing else. Cannot jump gears. Constraint or requirement?
That's both, because if it jumps gears, the system's going to die, and that's how we want it.
It's a constraint. Shifts with the push of a button. Requirement or constraint?
Requirement.
Requirement, right? So requirements are to do with the functionality, and constraints are to do with the limitation parameters within which you have to get the required functionality accomplished. Okay, so all right, slide 7. So one thing, please consider having a white background because I really can't tell the difference between dark blue and black. So a higher contrast would be really good. I like this diagram. How come after 4 years we still don't know where the outlet is for the air tank?
Well,
this is part of your design. That's required information to get the design done. You need to find that out.
I have a picture of it. Like I know where it's at, but it kind of depends on what angle it's coming out of and stuff. Like if it's
right. So you need to talk to, you need to talk to Mr. Carlson to get that information because otherwise you can't have a final design, right? Okay. 9. All right, we have a problem here, okay? Christian cannot do all the electrical work because if you go to slide number 10, he has more than double the work of some team members. That's not realistic. So some of the ME folks will need to take on part of the electrical tasks, okay? You cannot, you need to level your load a little bit, and this is not a leveled workload.
Yeah, we specified that whenever we were presenting.
Yeah, but just because he is electrical doesn't mean that he gets to do all the electrical stuff. You've seen other ME projects that have electrical tasks that don't even have an electrical engineering person on the team. So, you cannot really separate them that much. Okay, slide 14. By the way, if you're using Arduino board was not intended for electrical engineers. They were intended for non-majors. I mean, it's relatively simple to learn and do. So, I expect to see some contribution from the non-EE member of the team. All right, this one was, again, resource allocation loading. There's no resource leveling at this time, so I'm not sure what I'm looking at. There's no leveling. Slide 15. So you mentioned your key at the very end, so we were all waiting to figure out what A, B, C through K is. You need to find a way to squeeze your key into that white space, okay, so that I can do a visual reference of going back and forth. But very concise, everything is there, but I don't know what I'm evaluating except for those main captions. So make sure that your key comes before and during those slides. Okay, slide 24. Good job. I think this is Kyle's work. Good job, Kyle. 9 data points, 1 for each month. For month 2 and 3, you're right on track. It looks like, because probably there wasn't that much expenditures or that many hours. And then you're slightly behind because you haven't put much work in the last month, which is okay. But you'll have to pick up speed. I liked how you are going to move forward and not wait till January, because those risks that you have identified are real and can hit us anytime. So I appreciate the fact that you want to purchase things right now and try to beat any COVID-related issues that may show up. So good job, everyone. I've seen improvements in all the presentations. I'm very pleased. All the things that we've discussed are nitpicking things, and I'm only mentioning them so you have a chance to improve both your PowerPoints before you submit them. And then the reports, like I said, I'm really behind those. I'm going to do my best to get as many of them done as I can this weekend. And most of it, your 80% of your final report is the same as your progress report. So the main differences will be the monitoring and audit plan and control and audit plans. Those are the new stuff. So I'm really pleased. Again, I'm very concerned about some of the projects I've seen so far about the timeline. It's okay to be behind right now, but you really need to have a good plan to make up for that missed time. And if you don't plan on getting, working on this during the 2.5 month break, we have a problem. So please plan to get some things done. All right, in the 13 minutes, I'm going to discuss engineering ethics. So I'm going to take back, thank you for that. I'm going to share Blackboard with you. And again, this is important for engineering technology folks also, but you don't have to do a new assignment. What we discuss right now is going to help you as well in your assignment. So let's see why I'm unable to share my screen. Can somebody give me, okay, that's because change role to presenter. Okay, we're in business. Okay, so this is under, well, I'm going to go to the right class for this. So under assignments, and again, ENTC students, you have already gotten this assignment. I'm doing different examples today so that it's not redundant. And your assignments will be different than this class's assignment. Okay, I want to spend some time on National Society of Professional Engineers Code of Ethics, which is actually a standard for this organization. And I'm not going to read this, but I'm going to highlight it for you. It starts with why we have Code of Ethics. Engineering is an important and learned profession, and we have responsibility as engineers, okay? And then it has fundamental canons. This is engineers in the fulfillment of their professional duties shall hold paramount the safety, health, and welfare of the public. This is number 1, subsection 1, okay? So that's the first thing that the Code of Ethics dictates. And then it says you perform services only in your area of expertise and competence. And then you only issue public statements in an objective manner and truthful manner. And then avoid deceptive acts, conduct yourself honorably, responsibly, ethically, lawfully. The second one is rules of practice, and it relates to the fact that engineers shall hold paramount. We just talked about safety, health, and welfare. So that comes back again, and it goes into details what that entails. Okay, so when you are reading an ethics case that is presented to you, you evaluate the case and what people have done, and they're asking you, well, was this ethical? You need to go back to this standard and base your decision on this, so that if I'm from, South Africa, New Zealand, Middle East, some other country, we are basing our decision on exactly the same concepts, because sometimes people get ethics confused with morals. Morals are very personal and very cultural, but ethics should be standard. Okay, number 2 is engineers shall perform services only in the areas of competence, and it explains how engineers are to undertake assignments only when qualified by education and experience to do so. Again, issuing public statements, truthful, unbiased, all that good stuff. All right, and then professional obligations. One more. Number 4, engineers shall act for each employer or client as faithful agents or trustees. So here's the challenge about engineering ethics. You may have some of these canons that may, in some situations, conflict one another. So what if you have to choose between the health and safety of the public or keeping things under a lid for your employer if something went wrong at work, because you are to act as faithful agents and trustees of the employer. So what do you do, right? So the safety of the public comes first. And so we may have situations where some of these may find themselves in conflict with one another. And that's why we have case ethics committees to do this analysis. They're not always that straightforward. Engineers shall avoid all conduct or practice that deceives the public. Engineers shall not disclose without consent confidential information. And then there are some additional things. They will not be influenced in their professional duties by conflict of interest. They shall not attempt or obtain employment or advancement of professional engagements by untruthfully criticizing other engineers. So you can't go and say, this engineer's work is not good, just hire me and I'll do a better job. You can't do that. Obviously, you cannot attempt to injure or harm anyone that's given. And believe it or not, some of these were added later on because there came about a need for them. So they're not just out out of blue. Engineers shall accept personal responsibility for their professional activities, provided, however, that they may seek indemnification of services arising out of their practice or for other than gross negligence. So remember, we talked about how only one person is responsible for a given subtask, right? This is so that you can be accountable for it if a situation arises. And of course, you have to give credit when credit is due. And then, so the assignment is, let's go back. I've given you 3 ethics cases. This is for the engineering students, engineering technology students have 3 different case studies. They're all from the same place, and they're all the same weight. So none of them is easier than the others. Okay, so you will read. Let's take a look at the first one. This is objectivity, truthfulness. Engineer A, this is a ethics case. Engineer A is a consulting engineer who performs structural inspections using mechanical drones. The scope of Engineer A's services is solely to identify the physical conditions of the bridge and make recommendations regarding bridge repairs. Engineer A deploys a drone to perform a series of bridge inspections as part of his contract with the State Department of Transportation. During one of Engineer A's drone inspections for the State Department of Transportation, the drone unexpectedly records an encounter between a law enforcement officer and a motorist that results in exchange of gunfire. Following his review of the drone recording, Engineer A relays it to the State Department of Transportation, noting the gunfire event. The State Department of Transportation advises Engineer A that it does not plan to share the information with state or local law enforcement unless so requested by state or local authorities. What are Engineer A's ethical obligations under the circumstances? So your assignment is to go back to those canons that I've just read and identify at least 3 or 4 subsections that apply to this case as to what the Engineer A's ethical obligation is. So to give you an example, there's an ethics case study example. Okay, this is from the National Society of Professional Engineers. I don't expect you to do an analysis that's 2 pages long like they did here. But what I do expect you to do is identify the NSPE Code of Ethics that's relevant to your justification of what the engineer should do. So let's look at this one real quickly. This is about potential infringement of patent or intellectual property in a foreign country. So Engineer A is a professional engineer in country X and heads the product development division of some pharmaceutical company. This country has experienced a serious problem with infant deaths resulting from an infectious but curable disease. You have physicians in this country that have who have prescribed drugs to address this infant disease, but the supply of drugs in this country is often inferior quality. And so what the company does is it purchases some equipment and it develops this drug that is protected by patent law in the country that it was invented, but it is not protected in the home country that it is being used. Okay, so what are Engineer A's ethical obligations under the circumstances? So Engineer A is assigned by this country X the responsibility to do this manufacturing based on country-wise patent. Okay, so the parts that are applicable, you'll find this in the ethics code. Engineers shall hold paramount the safety, health, and welfare of the public. Then engineers shall give credit for engineering work to those whom credit is due and will recognize the proprietary interests of others, which means you need to recognize someone's invention. And engineers, so there's some conflict there, right? There's a conflict, so you need to figure out which one is the right one. Engineers, before undertaking work for others in connection with which the engineer may take improvements, plans, designs, inventions that may justify copyrights or patents, should enter into a positive agreement regarding ownership. All right, so here's what the ethics committee found relevant, and here's their 2-page discussion of what the engineer should do. So they decided that Engineer A had an ethical obligation to respect the intellectual property rights of this other company in country Y, to take appropriate steps to address those rights. Such steps should include seeking clarification and finalize. Well, you don't need all that, but basically the engineer should respect the intellectual property rights of the inventor in the other country, even though those intellectual property rights are not protected in country X. So that's the conclusion. So I'm just looking for one paragraph, but I'm looking for at least 3 or 4 of these code references that you use to come to your judgment. You can work in teams of 2 or 3. That's highly encouraged, so I don't have to grade 50 different submissions. But please, if you're working together, make sure you have a cover page and everybody submits the same assignment so that I don't, by mistake, grade everything again. That's all I wanted to cover. Does anyone have any questions? And I'll give you until the last class day to submit this. Same thing goes for the ENTC folks, okay? Any questions?
Would you say that those cannons are in order of priority? Because they do have health and safety first, but
they did, didn't they? Yes. Well, that's difficult to say. I mean, this is why we have whistleblower protection laws, because whistleblowers actually are going against that 4th canon where you are trusted agent of your company, right? And you're supposed to act as such. So, yeah, I would say that public safety comes first.
Okay.
But again, I mean, you can argue. That's why they have committees, because they're not just clear. All right, Frank, you have a question?
Actually, it was answered previously by Nathan's question. I was going to talk about the Challenger flight tragedy that happened several years ago, and how several engineers were against the final decision to take off on that day due to the temperature decrease. So yeah, he answered the question already.
Absolutely. So public safety comes first. Yes.
Sure.
Any others? So again, please work in teams of 3. They don't have to be the people on your team, because this is a, independent assignment. I need this for ABET accreditation documentation. So that's why it's so late. And we'll do more of this next semester, but I need an example for this semester.
And when does this due?
Last class day, which is 24th of November. So right before you go out for your Thanksgiving break.
Okay.
Also, please be on the lookout. There may be a sudden announcement that final exams may not occur face-to-face. I'm not sure if that is the case, what the alternative will be, but just be aware that things are changing very rapidly right now. And then just please be flexible, okay? Any other questions?
Dr. Rubin,
all right.
Were we gonna?
I'm sorry.
Were we gonna meet on this link, or did you want to go to the?
We can meet on this meet. I'll just wait one more minute for any questions, and then I'll start kicking people out if they just forgot to log off.
Okay.
Thanks, everyone.
I wish there was a way to mute all the sound notifications. Like I hate that.
Dr. Rubin, can you hear me?
Yes.
Okay, awesome.
Go ahead.
I wanted to try to go back and double check all of the improvements that we need to make for the grocery carrying UAV presentation.
Okay.
So, yeah, one of the main things we've been concerned about is finalizing a design, because obviously it would be really unwise to not work during those 2 months.
Yeah.
But we've mentioned that in our meetings, but we've been mainly focused on the design so it can meet criteria. And of course, our budget has been a really big focus point. So our last meeting, everybody did decide or conclude that they'd, be able to.
You have to chip in.
Right. The only problem now, which we're moving on to, is getting everybody, because we have multiple members that are not in Corpus Christi right now. So we're figure out, time schedules to fit the work or the labor.
Right.
So that's
also,
one thing
what you
we're going to
can
adjust
do.
to.
Right.
Yeah.
So another thing you'll need to do is probably modularize the tasks so
Right.
that each person can work on sub components independently and then you integrate in the end. Because obviously not everybody can work on everything at the same time. So
Yes, ma'am.
Yeah.
Right. Okay. So let's see. I know we've gone over the design. The feasibility you said was good, but we needed to apply actual evidence.
Yep.
Okay.
Yep.
I had a question about the linear responsibility chart. Now I had it numbered 1 through 6, and for the most part, everybody does have a responsibility for each
Yep.
task. The only one was the weekly meetings, which I know you said
Right,
is
but
me,
who
the
is
project
responsible
manager.
in scheduling them? Because when you
Right.
put weekly meetings, if it's a task, it is using resources and somebody scheduling them. So just meeting is not a task; it's a deliverable, right? It's one of those things that don't require any resources. So you don't need to allocate resources for meeting because that's something that you have to do. It's kind of like, remember on the AON, AOA diagrams, it's the dotted line. It doesn't take resources. So what does take resources is setting it up. So
Right. Okay. I'll have to revisit that part then.
yeah, and don't worry too much about it. I'm not too concerned about it. And that's the last time we're going to see this is the final project. Next semester we're going to drop that. So don't waste too much time on it.
Okay. And then
All right.
I had one last thing. For the earned value chart. Now I was incorporating like the hypothetical costs for completion of everything we've done now. So we made a mistake. It's actually 16 hours that the group has contributed to actual work.
Okay, so you need to remember in the Gantt chart.
Right.
When you define a task, you define when it starts and when it finishes, and then you can allocate hours for each person for that task. And when you're doing earned value, you can then cumulatively calculate how many hours those tasks are going to take. So your Gantt chart and earned value chart needs to be in perfect alignment. You can actually get the earned value from your Gantt chart if you have put in the hours for each of the tasks. And so it may be that you can get some tasks done in less time than you planned, in which case, you'll have positive variances. And I'm only asking for you to get 9 data points, one for each month, so you can combine them. But you need those hours in the Gantt chart, if you're going to use MS Project to create the earned value chart for you.
Right. I think that's actually why I used Excel, was partly because of some of the tasks were scheduled for a certain X amount of days when they could have actually been done sooner. So I think that's something we're going to have to revisit and edit.
Sure. And I think it'll help you with your monitoring and control plan too, if you put real data in the chart. So.
Right.
Okay. The only thing that carries over next semester from planning purposes, you still need your background, you still need your problem statement and, your scope and all that. But as far as what carries to next semester is going to be your Gantt chart. We're not going to look at AON diagrams. We're not going to look at linear responsibility charts or anything like that. So the Gantt chart is the one that really, really needs to be the right one.
Okay.
Okay.
Yes, ma'am. Thank you.
You're welcome. Anyone else before I kick people out?
I have one.
Okay.
So no one here is on my group, so I feel like I can speak openly. One of my group members is dead set on having our frame be 3D printed, and I cannot convince him enough that it's the stupidest thing I think I've ever heard of. I mean, making something that's 3 inches tall takes all night.
It's going to be really expensive to print such a big part.
Exactly. And he thinks that just because we have a $2,000 budget that we can do things like that. And I keep trying to convince him it's expensive, it's time consuming. If anything breaks, we have to reprint the entire part.
Yeah.
I was planning on doing either aluminum or an alloy of some sort. And I have a welding machine at my home. So even if COVID were to hit, we could still do this
Yes.
complete thing in my garage, no problem.
Sure.
I'm just trying to figure out what would be a good way to just be
Okay, did you
respectful, 'cause
discuss
I'm about
this
to
with
lose
you?
myself.
Sure. Did you discuss this with Dr. Baca as a team?
Briefly, but we haven't really had a full sit down discussion about all of this. What we normally
Okay.
do is we have our meeting and we just give him the minutes after the meeting. So we haven't
Okay.
had a conversation about the frame yet.
Okay, so let's your team and I meet next week. Send me an email of a time that works with everyone. I prefer it to be during my office hours, but if not,
of course,
I'll meet with you in the late afternoon. And then let's discuss it. Okay.
Thank you so much.
You're very welcome.
I think there was one more thing. Oh, the feasibility portion of this. When you say the technical, economical, social, are you wanting us to talk about every single one of those or just the ones that truly apply to our project?
Oh, every one of them, because trust
Every
me,
one of them,
everything
okay.
applies. Everything applies. Yeah. So
All
the
right.
the social impact would be, how would your design change the behavior of the society, which means you're introducing this design and everyone's going to like it, and therefore they're going to look at rehabilitation a different way based on
Y'all,
your
can you close
design.
that door? I'm sorry.
Okay.
Work is having a
All right. I do have a meeting after this, so, and I don't want to rush people, but
No, you're fine. Stay with us. Enjoy your day.
all right.
Bye-bye.
Bye.